So, hello friends. Here we have the lab power supply that I have been working on over the course of the last, I guess, 3.5 weeks, and it is now finally completed. And in an earlier episode I have shown you how I tore down an old broken audio amplifier, reused some of the parts I found inside, added a new front panel, and two commercial switching converters, the control elements of which you can see on the left and on the right side of this device. But here in the middle we have two meters, one for a voltage and the other one for a current measurement, as well as two potentiometers and two mounting posts that I added to this device as well. And they are the control and measuring elements of a linear regulator and, well, let's say the more traditional approach to a lab power supply. And how I built that and how that works is the topic of this video.
So let me briefly reiterate what happened in the last video, beginning at the point in time where the old audio amplifier had been torn down completely. And let me then show you the changes that I'm going to make in this video. Now, we started with a transformer, an ordinary mains transformer, that is connected to the 230 volt grid via an on-off switch, a fuse and a thermo switch that was already integrated inside the transformer. On the secondary side we didn't find one or two, but actually 4 secondary windings, and because those 4 secondary windings were soldered together in pairs outside of the transformer, they created virtually 2 windings with center tabs. And what I did with the first 2 windings is to separate them and connect them in parallel so that a single positive voltage rail could be derived via a bridge rectifier and 2 large electrolytic capacitors that were connected in parallel. They were then followed by a buck converter and a boost converter that can be engaged or disengaged by individual switches. And in this video I'm now going to add a third converter, this time a self-made linear regulator, to that power rail. And because the 2 switching converters will play no role in this video, we will just blank them out for now. And just by the way, the circuit that you see today is enough for a standalone power supply, no matter if you want to use a buck and boost converter additionally or not. But the linear regulator must be designed in such a way that it can be adjusted from really 0 to 30 volts. And in order to make that possible, I need auxiliary voltages. And I do that by using the 2 remaining secondary windings on the mains transformer. But this time these 2 windings will be kept connected in series, a bridge rectifier is connected to them, and the center tab is referenced to the circuit, but not connected to the chassis ground as some might expected, but to the output voltage of the linear regulator that I have called VO3 in the last video. And a lot of the parts will be referenced to VO3 and not to the actual chassis ground, as you will see. Following the second bridge rectifier, we have a small integrated linear regulator 7805 that gives us a plus 5 volt rail in reference to the output voltage. And then we have a second branch with a 7905, which is the negative counterpart to the common 7805, and we have a bunch of capacitors here again for filtering and to operate these 2 linear regulators more ideally. One side note here, if you want to use linear regulators like these, they always need a minimum load resistor because they are practically dynamic voltage dividers and the voltage cannot be divided if there is not a load attached. If you want to know more about this, then please watch my video SMPS tutorial part 2 linear regulators, where I derived the idea of the linear regulator from a plain old voltage divider. And here you can also see the type numbers and actual values of some of the components that I used in this circuit. And you can see that the 2 large filter capacitors have a rating of 4,700 microfarads each, adding up to a total capacitance of 9,400 microfarads. And I simply used these capacitors because they were originally used in the old power supply inside the audio amplifier here. And some people might have the tendency to add even more and more capacitance to an input rail like this one. But, well, the job of the linear regulator is to stabilize the output voltage. And as soon as there is a voltage drop across the series transistors of the regulator that is large enough, it is not necessary to add any more capacitance to the input side of the linear regulator. It can sufficiently regulate and stabilize the output voltage so that there is virtually nothing left of the ripple that is derived from the frequency of the grid. By the way, if you want to build this yourself and you don't find a transformer that has actually 4 secondary windings or 2 secondary windings with center taps, you can use a second auxiliary transformer and connect the 2 primaries in parallel. The VO3 plus 5 and VO3 minus 5 rails are going to play a role in the circuit of the linear regulator, and we're going to take a look at that right now. So, all we have at this point is the voltage VI across the 2 large filter capacitors. That voltage is unregulated, which in this case means, to be more precise, that in addition to the constant DC voltage component of VI, there also is a so-called ripple voltage, an alternating component that is superimposed to that constant voltage.
So here we have some video footage of much later in the development process of the lab power supply. But the dummy load on the right, as well as the inputs of this old oscilloscope and this digital multimeter, are directly connected to the large filter capacitors and are measuring or displaying the measurements of the voltage across those capacitors. And what we can see on this screen here is the delta V between the maximum and minimum voltage in each cycle. And on this readout here, we see the mean voltage across those capacitors. And in this case we're now having a lot of load on here, but let me show you how relatively smooth that unregulated voltage is without any load, and then we're going to burden that source step by step with more and more load. 1 volt per division, 500 millivolts, 200 millivolts, 100 millivolts, 50, 20, 10, 5. So here we are at 5 millivolts per division, and we are counting around 1, 2, 3, 4, 5. So we're talking about 25 millivolts of delta. So I have now set the sensitivity back to 1 volt per division, and you will hear some clicking sounds, and those are the 5 dummy load resistors that are being switched in parallel successively. And resistor 1, resistor 2, 3, 4, 5. So we're talking about 9.4 ohms of dummy load resistance here, maybe a little more or less. But you can see that we have a delta of, well, around 2 volts. So here you can really see what I mean when I said that the voltage across these filters is unregulated. And also the DMM shows us a mean voltage drop around 4 volts DC. And that is because of the internal resistance of the voltage source that the rectifiers and these filter capacitors represent. And let us try to get a total readout here. We're going from AC to DC coupling. So here we can see that the peak voltage or the bottom voltage here is still somewhere over 30 volts, but it gets kind of close to the maximum voltage that the linear regulator is specified for. So maybe adding a little more capacitance would help a little bit, but well, it would actually be better to have a transformer with a few more windings on the secondaries.
Okay. In order to really understand what is going on here, we actually would have to take a look at the equivalent circuit of this portion of the lab power supply and explore the various non-ideal properties of the components used here. But I actually want to wrap it up here and get back to the actual design that I want to use and to the building process of my power supply. But there are still a couple of things that you can keep in mind here, even without understanding all the details. One, we saw that even when no external load was connected to the power supply, the voltage across the filter capacitors was not really constant, meaning that the capacitors were kind of discharging themselves over time. We then saw a periodic behavior in the up and down of the voltage across the filters, and that shows us that there is no constant supply of energy from the grid side, but that the filter capacitors are charged in bursts of current. We then saw that as the output current through the dummy load was increased, the mean voltage measured across the filter capacitors sharply dropped, telling us that this portion of the circuit acts like a very non-ideal voltage source with a comparatively high internal resistance. And the linear regulator is going to take care of all of these problems, and it will additionally allow us to set the output voltage to a fixed value lower than the voltage across the capacitors. So let us explore how the circuit does all these things. First of all, we have a power transistor, to be more precise an NPN type Darlington transistor, and its collector is directly connected to the plus pole of the input filter capacitors. The emitter of this transistor is followed by a network of shunt resistors, to be more precise 4 in parallel with 2.2 ohms each, and they comprise one 0.55 ohm resistance. For now, let us ignore the role of this shunt resistor though, as its resistance is very low and does not influence the behavior of the circuit very much at this point. The other end of that shunt is connected to one of the mounting posts on the outside of the power supply, where then, at this moment, our dummy load is connected and where later real loads could be powered. And what you see here is the collector-emitter path of the transistor and the actual load resistor forming a voltage divider. And the voltage VO3, that is always a fraction of VI, is kept constant by a regulated current being fed into the base of the so-called series transistor. So in other words, this virtually works like a dynamic voltage divider, where the collector-emitter path of the series transistor acts like a variable resistor that is at very high speed adjusted to fluctuations in VI or in IO3, that means in the current flowing through the transistor and through the load, thus keeping either the voltage VO3 or the current IO3 constant, depending on which part of the regulation is actually in action. But of course, in this picture you cannot yet see any of the circuit that actually regulates that. We will see that in just a second. And just on a side note, what is a Darlington transistor? Well, it's actually a kind of integrated component that has actually two transistors, the gains or amplification factors of which can be multiplied. And a Darlington transistor is typically a power transistor with a smaller driver transistor connected to it, which makes it unnecessary to have a discrete driver circuit in order to supply the necessary base driver current for that large transistor. It also has a protection diode built in and a couple of resistors, but they do not play a large role in the circuit. But in short, you could say that a Darlington transistor acts like a power transistor with a much larger amplification factor. And the transistors that I am going to use here are TIP or TIP 142, and you can see some of the typical values from the datasheet of the transistor right here. And because I want this circuit to be able to deliver relatively high currents, we have to allow for a lot of heat dissipation, and that is why I'm not just using one of these Darlington transistors, but actually 4 paralleled Darlington transistors, and each of these transistors has a network of shunt resistors in its emitter path. And well, these shunt resistors will serve a double purpose in this circuit. One is that if you want to parallel bipolar junction transistors, you typically insert a shunt resistor into the emitter path in order to counteract individual differences between the individual transistors. Not every transistor, even of the same type, is exactly the same. And in order to counteract that, you typically insert these resistors in the emitter path. It is then also necessary to add a little bit of capacitance to the output side of the linear regulator. And I'm using here a 10 microfarad plus a 47 microfarad capacitor. And these are values that I determined by experimentation. So maybe that can be optimized more. In short, you want to have a relatively low capacitance at the output side, because if very sensitive equipment is connected to the output, the capacitors could simply discharge into the output load without the regulator being able to do anything about that, and that in very special circumstances could damage the load attached. But it must be high enough so that the regulating mechanism is able to keep the output voltage constant. Furthermore, a voltmeter will be inserted into the device so that we have a readout of the actual voltage at the mounting posts. And then later on, an active current sensor will also be inserted into the current path in order for us to have a readout of the output current. But more about that later in the video. So these are just some of the most fundamental components of this circuit. But there is no regulation yet and no circuit that feeds current into the basis of the Darling transistors. And for that, we first have to establish a constant current source. And for that, I'm going to use this very simple yet very effective single transistor design. It is an 8 milliampere constant current source that relies on the BC556 universal type PNP transistor. It's a German type number, so if you can't get it, just look for BC556 replacement type or just use a small PNP universal transistor, whatever that is in your country or part of the world. And at the base we find a 2.5k ohm trim pot that is set so that ICC, the constant collector current, is around 8 milliamps. But if we left it all like this, ICC would just flow into the basis of the series transistors unhindered, and minimizing the resistance of the collector-emitter paths of these transistors and basically pulling VO3 up to VI so that we would be at the maximum output voltage basically all the time. So what we're going to do now is to build regulators that will divert a portion of those 8 milliamps so that they do not flow into the basis of the transistors, resulting in a higher resistance of the collector-emitter paths of these series transistors, which equates to a lower output voltage of the linear regulator. And I have now created two alternative paths where the current coming from the collector of the constant current source can go other than the basis of the series transistors, and those are the output stages of two ordinary op-amps. And the two diodes assure that there is no current going to be sourced and flowing outside of the outputs, but it is really only a portion of ICC being allowed to flow through the diodes into the output stage and being synced by these op-amps. And they are just two op-amps inside an ordinary LM324. That's a standard quad op amplifier, and that's why it says 1/2 LM324 to the left of both of them. And further to the left you can see that the upper one is our current regulation amplifier, while the lower one is the voltage regulation amplifier. The two 22 picofarad ceramic capacitors that are connected between the output and the non-inverting input of the op-amps are simply there to suppress possible oscillation of this amplifier. Other than that, they are used here at their maximum gain. And what the voltage regulation amplifier essentially does is to simply compare the output voltage VO3 to a reference voltage that is derived from this rather complicated looking voltage divider here. It might have a couple of resistors, pots and capacitors, but it really is nothing more but a voltage divider that was adjusted and designed so that the linear regulator can be operated between the specified margins of 0 and 30 volts. And if you want to use the circuit for higher voltages, you simply would have to change a couple of these resistive values. And I'm not going to explain here how every single of these values is derived. But if you were to build a circuit like this yourself, simply try changing some of these values and see what happens. The 1K ohm trim pot is adjusted in order to set the linear regulator to its absolute maximum value, here 30 volts, and the 100 kilo ohm voltage adjustment potentiometer here is one of the two potentiometers on the front panel of this device. The current regulation amplifier really compares the voltage drop across all of the shunt resistors to yet another reference voltage that is again derived by a rather complicated looking voltage divider. And here the 10 kilo ohm potentiometer is the second pot on the front panel, it's the current adjustment pot, while the little 250 ohm trim pot is used to set the maximum current that is allowed. And here again it is possible to redesign the circuit for currents of 5 amps or more by simply changing the shunt resistor values, and that is actually the reason why I have used 4 parallel shunt resistors in each branch of each single series transistor, because I was experimenting and tried to set everything just right for 3 amps of output current. In order to have a current readout at the front panel of the device, I used an active current sensor, which is basically a small current transformer with an integrated circuit made by the German company VAC Vakuumschmelze, VAC Vacuum Foundry. And well, it's a special component that we will have to talk about in a later episode, but I'll show you a little bit about that while building this device later in this video. So here we have basically the entire circuit of the linear regulator, and I hope that I didn't forget any of the resistor, capacitor values or type numbers. And after all the plans had been made, the circuit was implemented on the very Vero board that I had already used in the last video. And the two plus and minus 5 integrated linear voltage regulators were mounted onto the heatsink and soldered to the board. Then 4 Darlington transistors were also bolted to that same heatsink. And if you take a closer look, you can see that these are actually transistors in TO220 packages, and that they are not the TIP 142 types that I used in my circuit diagrams. Now the reason for that is that I originally used other transistors, which I later in the process replaced by the TIP 142s. The same goes for these large power resistors here. I had salvaged them from the original Sony audio amplifier and wanted to use them as shunt resistors in my linear regulator. That would have worked, but during the experimental phase I had to change the values of the shunt resistors several times, and that's why I ended up with 4 paralleled 2.2 ohm resistors instead. And all of the parts were step by step added to the circuit board, and well, some of it still had to be tweaked and optimized until it finally came to the point that you saw in the circuit diagram just a minute ago. In the next step then, a process followed in which I converted a 40 volts DC voltmeter into an amp meter for up to 4 amperes of current. And well, the details of how I did that will be covered in a standalone episode and are too extensive to be jammed into this video here. The same goes really for the current sensor that I also added to the circuit, which is also worth of its own video. But in order to make it short, I tried to measure the current by simply measuring the voltage drop across the shunt current resistors, but it turned out that the currents are not totally equally and symmetrically diverted and shared by the 4 series transistors. And for that reason, the voltage obtained by the regulating mechanism is not strictly proportional in a linear way to the current flowing through the entire circuit. And that is why the reading that I first obtained was a little off. And in order to solve that problem, I added the current sensor to the output of the lab power supply, because I had recently found a very cheap source for these. But as I said, I will cover that in an extra episode. It still took some time to put it all together, and I'm still planning to add some fans to the entire device so that the heat can be better removed from inside the enclosure. And well, I'm still looking for two plastic knobs that fit on the actual axles of these 10-turn pots that I added to the front panel. But other than that, the device is now completely finished and operational, and let's just test how well it works.
Stepping up voltage from 0 to 30 volts at 9.4 ohms load and comparing the amp on the amp meter with the amps on the DMM. Slowly stepping up the voltage and recognizing that a multi-turn or 10-turn pot is better suited for fine adjustments than an ordinary single-turn potentiometer. And well, also recognizing that the factor between the voltage and the current that you can read here is 9.4. Dummy load, 5 47 ohm resistors in parallel switched over these relays can be activated with these little dip switches here. Resistors are disengaged step by step. 5 in parallel, 4 in parallel, 3 in parallel, 2 in parallel, 1 in parallel, 0 in parallel. Witness how the voltage stays exactly the same. Measurements before have shown that we are within plus minus 1 millivolt. Now stepping it up again. 1, 2, 3, 4, 5. Second potentiometer for current adjustments. Now turning that down, for example, to 2 amps, and we can see how the voltage is correspondingly going down. Now, more interesting case that we can see here is, let's go down to 1 amp. Okay, 1 resistor, 2, 3, 4, 5. The supply voltage goes down as the load increases to keep the current constant. Now adjusting the current limit to 2 amps, 5 resistors in parallel, 4, 3, 2, 1, 0. 1, 2, 3, 4. There you can see we reach 2 amps, the voltage goes down. Another thing stays there. So as you can see from those memos that I basically recorded for myself, the power supply works just as expected. I measured that with the Fluke 87.5 once more, and well, across that spectrum of really 200 milliamps to around 3 amps, the voltage stabilization works at plus minus 1 millivolt pretty much. So that's really all I can ask for a project like this. And well, the current stabilization or limiting also works within a couple of milliamps, and that is really all I need for really 99% of all things that I ever do. Now, of course, you could build a power supply for extremely sensitive equipment with lower currents and finer adjustments for those low currents. But the next thing that I'm really going to do in this realm of things, I will build another power supply. I've shown some footage of that before, where I have like massive transformers and a couple of buck converters that I built myself, and I'm working on that. Well, however, this video was already quite complicated for a lot of people, and that other video about the other power supply that is going to come will be even way more complicated, and well, the kind of knowledge that is required to understand what is going on is, well, going to go through the roof, really. And it's not just about you guys, also about me. Building this was extremely excruciating, and you gotta understand, it's not just building it, it's developing it. Even though I, of course, found a lot of material on this, I read a bunch of books, found a lot of commercial designs from back in the day, so the circuit is by no means my genius invention. It is just a, well, fitting an old idea to a very specific situation and showing people how it works. And the circuit might seem complicated, but it's actually quite simple. Can be built from very ordinary components, where maybe except for that active current sensor, but that is not required in order to operate this device. Well, long story short, the next couple of videos I think will be a little simpler in nature and a little less complicated, because I need a break from this, and a lot of you probably as well. But just so that you know, the work on the larger power supply continues, and we will then go on to talk about switching converters and so on. But that's probably still a couple of weeks away, because I'm pretty near the breaking point at the moment, and I have to spend my time with a little simpler things for a couple of days at least. So I hope you like this, and that some of you will try to build a similar circuit or a similar device, and I hope to see you soon.